All right, so we're able to go through the mechanics to figure out that the symmetry of the hydrogen 1s salts, right, for a planar AH3 molecule, D3H, is going to be A1 prime plus E prime. And we know there's three salts, okay? Two of them are the E primes, one of them is the A1 prime, the totally symmetric one. Here's where we finally get to something that I've been telling you for a while in chapter 5 we would get to. And that is the use of the projection operator to figure out what the salts should look like. Previously, I've just intuited, we've always just intuited what the salts should be like based on the symmetry. And then kind of after the fact, checked what they are. But some cases that can be very difficult, or I've just given you the salts, right? And told you, hey, look, here is how the symmetry works, and we can check it, and yes, the symmetry works. But we haven't been able to come up with it from scratch. You can do that. Just in the same way that in vibrational spectroscopy, we use the projection operator to visualize the bends and stretchings of vibrations once we had their symmetries. We can visualize the salts once we have their symmetries. So now we have their symmetries, so we're going to use the projection operator. The A1 prime salt, I mean, it's totally symmetric, so you know what it's going to look like. There's always going to be one totally symmetric salt. And in this case, you know, that's just going to be in a triangular relationship, trigonal planar relationship, all the s orbitals in phase, right? There's always going to be that totally symmetric salt. So we know what that looks like. But for the two degenerate E prime salts, it's pretty difficult to intuit what they would be, and I'll show you why. So we're going to use the projection operators to help us. Okay, so we did this previously for normal modes. There was this kind of complicated equation here that tells us how to use the projection operator. The annoying thing about this equation is that it is a sum across all operations, So that means not just all classes, all operations, okay? So that's gonna take some work. All right, and so what we're going to be using this for is the vectors, right? That's what we're gonna be applying the operations to. Okay, so I pulled up the D3H character table for us, pull up our little vector diagram. There's our definition of the projection operator. So we're going to do this for the A1 salt. Now, the nice thing is, always do it for the A1 salt first, because you know the answer for the A1 salt. You know that it's all the s orbitals in phase. It has to be. It's totally symmetric. One's across the board. So if you go through the mechanics and you get the right answer, you know you did it right. And so this one actually isn't that bad to visualize. So let's go through it. But notice first, right, I have these hats. The hats, remember, just mean operation, distinguishing it from like point group or a class. Okay, so I have the identity. I have a C3 operation. I have C3-2, because, right, C3 twice. What does this 2C3 mean? It means there's a C3 and there's a C3 twice. And then I have the 3 C2s. Okay, I call those C2, C2 prime, and C2 double prime. Those are the perpendicular ones. There's only one sigma H, I've got that. And then there's two S3s. Which ones are those? Those are S3, and it's actually S3-5, or here I've called it S3 prime, just through a different location. It's the counterclockwise version. And then we have 3 mirror planes. I call those sigma V prime, and sigma V double prime. So let's go through this. First of all, so we're going to apply the these operations to all these vectors, okay? And then we also are going to multiply the result by the character in A1 prime. Now the character for all the classes is 1, so that's why we have 1s across the board here. All right, so let's go through this and see what we get. The first one is identity on V1. Now we know that the identity on V1 is just equal to V1. So we have 1 times V1, that gives us V1. Next, we do a C3, okay? Well, C3 is going to, if we define it as clockwise, which again, if you do counterclockwise, you'll still be okay. because things will end up canceling each other out. But V1 is going to go to V2. So we have V2, we have 1, right? There's the 1 there. We have 1 times V2. Next one is C3 twice, okay? So C3 twice, that's a 240 degrees. V1 is going to go, here is C3 twice. V1 is going to go to V3, okay? Next one is our C2, okay? So we can define this kind of, there's 3 C2s. We can define it however we want. First one I'm going to define as this one, going through V1. So if we go through V1, V1 stays the same. And so this one right here is V1, right there. Next one is a C2 prime. C2 prime, I'm going to call it this one. Let's see. Yeah, let's do that one. And there's a C2 there. That's going to take V1 and spin it, right, to V3. So this C2 prime became V3, and there it is. Okay? Next one is C2 double prime. Last C2, that one's going to be going through V3. And so when we spin it, V1's going to go to V2. Again, this is a C2 double prime. There it is here. And our V2 is right there. So we got that one. We're done with the C2s. Next is sigma H. Sigma H, that's in the plane of the molecule. That's going to do nothing to all the vectors. So that's why we have a V1 right here. Next one is S3. S3, we can do one where we did a C3, okay, that way, C3 that way, right? It's pointed down, there's the C3. And so that is going to take V1 into V2, and then we do a sigma H. Sigma H, we just established, did nothing. This is in the plane of the molecule. So overall, that's just going to get us V2, which is right there. The next one does V3. Why is it? It's because it's a counterclockwise version of that, or we can call it C3 twice. So V3, it's basically, it's S3 5. Okay, that's technically what it is, but that's a C3 twice, sigma H. We can go through that. And anyway, that's going to get V1 into V3. When you do a C3 twice, sigma H does nothing. So V1 went into V3 right there. Okay, so we're done with the S3s. Let's erase everything. Go back. Where are we? We are on sigma Vs. We only have 2 more left. Sigma V1. Okay, so we got a V1. So that one was the plane defined like that. Okay, it took V3 and V2, interchange those, but we're applying the operation to V1. Why do we apply the operation to V1? It doesn't matter. You just have to choose one of the vectors. Okay, you can choose V1, V2, or V3. You just have to apply them all to V1. Okay, you only have to do one of them. So that's the V1 there. The next one is another mirror plane, and I chose next this one. Again, doesn't really matter the order you do these things in within a class. So that's going to take V1 and V3 and interchange them. So that's why I have V3 here. And the last one is this one going through V3. And so that took V1 and went to V2. That's at the bottom. You add all these up, and you're going to get 4 times V1 plus 4 times V2 plus 4 times V3. Divide out the 4s. You got V1 plus V2 plus V3. They're all in phase. They all have the same magnitude. It's totally symmetric. We got the right answer. We can take a deep breath and be happy with that. Now, the beautiful thing is, to get the ESALCs is very, very easy. Okay, at least to get the first ESALC. Now, I'll show you why the second ESALC in a second is a little hard to get. But to get the first ESALC, it is no problem. Why? Because we did all the hard work of all these operations. All this, the formula stays the same, but now instead of having 1s across the board, we put in the E prime. Okay, this should say E prime solve technically. Okay, it says E. You got the idea. 2, -1, 0, 2, -1, 0. There it is. 2, -1, -1. Why is there 2 -1s here? Remember, we have 2 in that class. But there's 2 -1s, the zeros for the C2s, 2 for the sigma H. There's only one sigma H. 2 -1s for the 2 S3s, and then the 3 sigma V's get 0. And if you do all that math, and again, all this, the actual mechanics of moving the vectors, we already did all that. That stays the same. You'll get 4v1 minus 2v2 minus 2v3. Well, we can divide that by a common factor of 2 to get 2v1 minus v2 minus v3. What does that look like? It looks like this. One of the vectors, in this case v1, we put, is going to have twice a positive. I put it light. I could have put it dark. Doesn't matter either way. Just would have to flip these. But it's going to have twice as much electron density. The other two are going to have the opposite sign, but be half as intense. Okay, so the half is big. So we draw it like that. All right. How do you find the second solve? We only got one. And that is what I'm going to go over in the next video.